My name is Natalia Powers-Riggs. I'm a graduate student in Professor Michael Wazalewski's group in the chemistry department. And today I want to talk to you about my work in finding shortcuts to more efficient solar cells. The sun is an exciting possible source of alternative energy. It's safe, it's cheap, and above all, it's plentiful. In 1 hour, the sun hits the Earth with 96,000 terawatt hours, which is more than 5,000 times the amount of energy the world consumes in that same span. In fact, it's estimated that in just 1 hour, the sun hits the Earth with enough energy to power our needs for an entire year. Despite this, we're not using very much solar energy. In the past year, our nation only dedicated 11% of the energy we used to renewable sources. And of that, only 6% came from solar energy. Now, why is this? A large answer has to do with efficiency. In order to explain what I mean, I'll go through how a solar cell works. So what a solar cell does is it converts sunlight into electricity in the active layer, which is made up of various molecules. At this point, we have a sun that hits the active layer and absorbs one photon, or one packet of energy. This photon is then converted into an electron, which is able to be used for electricity. Generally, we have, an ideal system, one photon in, one electron out. It's a one-for-one deal. But most solar cells are not that efficient. Commercially available solar cells are only about 15% efficient of the energy that they're provided with. Why is this? The answers are many, but a couple of them have to do with the ability to do this conversion, in that sometimes the energy is not absorbed. Sometimes it's absorbed and released before it can be converted. Or even once the conversion happens, it's not able to be consumed in current. What I'm curious about is what kind of creative ideas can we come up with to increase the amount of efficiency in our solar cells? Now, efficiency is something that we think about a lot in day-to-day life, whether it's changing your gears on your bike to make things easier or to go faster, or coming up with a more creative solution to doing your homework. It's something that we want to do in order to maximize the output for a given input. We want to be able to get a lot out for whatever we put in. And what I'm interested in is seeing if there are similar creative ideas that allow us to get more energy out for the time we put in. So I have two shortcuts that I've used to try to find better ways to make solar cells. The first shortcut is a process called singlet fission. In singlet fission, we essentially have a 2-for-1 deal. Instead of having this one electron in, one electron out system, we've observed in certain systems that we can see one photon is absorbed and is then converted into 2 lower-lying energy packets, both of which can be converted into electricity, giving us essentially a 2-for-1 deal. We can vastly increase the efficiency of the system we have. Now, what do we need to do to get this system? Singlet fission, this 2-for-1 deal, relies on a couple of things. One is the molecules that we use. What are the materials we are consuming? In my lab, I've worked with terylene diimide, or TDI. It's this blue molecule, and it's stable to air, stable to sunlight, and has the right energetics. It has the right high and low energy packets. But what's also important, and possibly more interesting, is how these molecules are placed matters. You need 2 molecules to be close enough to have this interaction. But if they're side by side, nothing happens. It's only when these molecules are offset either vertically or rotated in relation to each other that we see this process. But how can we get this to happen? When we're building things at our scale, say we want to make something with this pile of bricks, we can make a number of different patterns. We can make a stacked pattern, we can do something with offset, or we can even build a helical tower. But when we're working with molecules, this just isn't possible. They're too small. We're not able to individually line up molecules in the way that we'd like. So what do we do? This brings us to my second shortcut. It's a process called self-assembly. The process of self-assembly relies on the idea of using small building blocks to make larger, more complex systems. This can occur through different kinds of linkers, where one molecule is set to link with other molecules in certain sites. And the shape and the size of that molecule can determine what kind of larger order we make. Even if bonds are made or broken in the beginning, eventually we can be sure that they'll make the most stable conformation at the end, something we can, again, predict. Alternately, we can have a system that relies on stacking. If we have molecules that are going to stack on top of each other, like the bricks, we know that they're going to create the same structure every single time. So in these cases, we can make either bricks that link together or bricks that will stack on top of each other without us having to place them individually. Self-assembly is something that's incredibly common. It's in our very DNA. On the left, we have a cartoon of what a strand of DNA might look like. We have nucleobases, 4 different kinds that always pair to the same things: G with C, A with T. These linkages count as a type of self-assembly. Furthermore, once in this long strand, they'll coil to create the double helix that we might be familiar with, which then will further assemble and stack to create the chromosomes that make up who we are. In my research, I took this idea of self-assembly from DNA, in fact, took one molecule in particular, this green arrow, guanine. Normally, it pairs with cytosine, but if you remove it from the context of DNA entirely, we can treat it as a linker for self-assembly. Normally, again, pairing with guanine, but in the context of other guanine elements, we can get it to assemble into a 4-fold structure. These structures are flat and can stack on top of each other, essentially creating a smart brick that, again, links to each other and stacks the way that we would expect it to. If I can attach another molecule, again, the TDI that I referred to earlier, I can create a much larger system. These TDI molecules are attached to the linker, and I can create a larger complex system that stacks with this helical design, essentially giving me the design that I was looking for, something where I can have offset and rotated molecules in order to see if I can achieve this 2-for-1 deal. I've worked really hard on making the molecule, and I'm right now starting to get to the point where I can look at the assembly and look at how light interacts. There's still so much to learn and so much to be gotten out of these systems, but I'm excited to be working on these, and I'm incredibly confident that at some point we'll be able to use these 2 shortcuts of self-assembly and singlet fission to make more efficient solar cells and take advantage of the sun and the energy that it provides. Thank you.